You know, I've spent decades studying this solar system of ours, and I keep coming back to the same realization. Without Jupiter, you and I might not be having this conversation right now. Not because it's close, not because it's flashy, but because that enormous ball of gas sitting out there, 5 times farther from the sun than we are, has been doing something remarkable for billions of years. It's been protecting us. Today I want to take you on a journey, past hurricane-force winds that have been spinning for 3.5 centuries, past moons that hide oceans deeper than anything on Earth, through magnetic fields so powerful they'd fry a spacecraft's electronics without the right protection. Let me share something fascinating. Jupiter isn't just the biggest planet in the solar system. It's the reason the solar system looks the way it does. Before we dive into the juicy stuff, I do want to acknowledge the people who make this kind of exploration possible, the supporters, sponsors, and patrons who keep the lights on and the questions coming. Science communication is a team effort, and every like, comment, and share you give tells the algorithm that people actually want to think deeply about the universe. So if you find yourself genuinely hooked by the end of this, go ahead and hit that subscribe button. Now, let's get into it. Let's start with some numbers because Jupiter's numbers are genuinely staggering. Picture 11 Earths lined up side by side. That's the width of Jupiter's equator. Now imagine stuffing more than 1,300 Earths inside a single hollow sphere. That's the volume we're talking about. Its mass is 318 times greater than ours, which accounts for a full 71% of all planetary mass in the solar system combined. All the other planets, moons, and assorted debris, together they make up the remaining 29%. And yet, for all that bulk, Jupiter is surprisingly lightweight in terms of density, just 1.33 grams per cubic centimeter, less than a quarter of Earth's. The reason is simple. The planet is made mostly of hydrogen and helium, the 2 lightest elements in the universe. Jupiter orbits the Sun at an average distance of 778 million kilometers. That's 5.2 astronomical units, completing a full lap every 86 Earth years. Its orbital shape is nearly circular, with an eccentricity of only 0.048, meaning it doesn't swing dramatically closer or farther from the Sun as some planets do. Here's something that always gets a reaction when I mention it in class. Jupiter spins faster than any other planet. One full rotation takes just 9 hours and 56 minutes near the poles, and a hair under 9 hours 50 minutes at the equator. That differential rotation, the fact that the equator and poles spin at slightly different speeds, is a key ingredient in the planet's dramatic atmospheric behavior. All that rapid spinning has also squashed the planet slightly. Jupiter's polar diameter is about 9,300 kilometers shorter than its equatorial diameter. As for seasons, there aren't any worth speaking of. With an axial tilt of only 3.13 degrees, Jupiter barely nods at its orbit. What you see is what you get, year after year. One more number worth holding on to. If you weigh 70 kilograms on Earth, step onto Jupiter's cloud layer and you'd register 168 kilograms. Surface gravity there is 2.4 times what we experience here. Of course, stepping onto Jupiter isn't actually an option, but we'll get to that. I've always thought of Jupiter as the solar system's most theatrical performer. That famous striped appearance, alternating light bands called zones and darker bands called belts, isn't decorative. It's the visible signature of an atmosphere in constant organized motion. The bright zones are regions where gas is rising. The dark belts are where it sinks. Running between them are powerful jet streams moving in opposite directions at different latitudes, and wherever those jets collide, you get turbulence, eddies, and storms. Some of those storms have been swirling for longer than the United States has existed. The most famous of them, of course, is the Great Red Spot. Italian astronomer Giovanni Cassini is credited with its first reliable observation back in the 1600s, which means this single storm has been raging for at least 350 years, possibly longer. At its largest, it was wide enough to contain 2 or 3 Earths side by side. It's been shrinking in recent decades, but it remains one of the most recognizable features in all of planetary science. The reddish color? Likely the work of sulfur and phosphorus compounds being churned up from below and then chemically altered by solar radiation. The atmospheric recipe is mostly molecular hydrogen, around 89 to 90%, with roughly 10% helium and trace amounts of methane, ammonia, hydrogen sulfide, and water vapor. The colorful bands we see result from photochemical reactions between sunlight and those trace compounds. Higher up in the atmosphere, crystallized ammonia forms the white clouds. Deeper in, things get stranger. As pressure increases with depth, hydrogen transitions from a gas to a liquid, and eventually, at around 10,000 kilometers below the cloud tops, into something called metallic hydrogen, where electrons flow freely through the fluid the way they do in actual metals. That metallic hydrogen layer, spinning rapidly along with the rest of the planet, is almost certainly what generates Jupiter's extraordinary magnetic field. You know what's interesting? Jupiter's magnetic field is 14 times more intense than Earth's, and it occupies a volume in space roughly 20,000 times larger. If you could see it from Earth with the naked eye, it would appear about the size of the full moon, even though Jupiter is hundreds of millions of miles away. Inside this invisible magnetic bubble, charged particles become trapped and accelerated into radiation belts that make our own Van Allen belts look modest. The radiation there is intense enough to pose a genuine engineering challenge for any spacecraft that dares to approach. Less intense but no less interesting is Jupiter's ring system. Most people think of rings and picture Saturn's grand spectacle, but Jupiter actually has rings too. They just lack Saturn's drama. Discovered in 1979 by the Voyager 1 spacecraft, the system has 4 main components: a faint innermost halo ring, a slightly brighter main ring, and 2 outer gossamer rings connected to the small inner moons Amalthea and Thebe. Unlike Saturn's rings, which are largely composed of ice, Jupiter's rings are built from tiny dust particles, debris knocked loose from inner moons by meteorite impacts. What lies beneath all those churning clouds? At the center, current models suggest a solid or semi-diffuse core composed of heavier elements, with an estimated mass somewhere between 7 and 25 times that of Earth. The uncertainty there is significant, and missions like Juno have been working hard to pin it down. What we know with more confidence is the layered structure above the core. Compressed liquid hydrogen above the metallic layer, giving way to a gradual atmospheric envelope. There's no sharp boundary where the planet ends and space begins. No solid surface to stand on, no cliff edge, just an ever-thickening envelope that gets denser and hotter the deeper you go. Humanity's relationship with Jupiter goes back to antiquity. It's bright enough to see with the naked eye, and was well known to ancient astronomers as one of the wandering stars. But the story changed dramatically in 1610, when Galileo Galilei turned his telescope toward the planet and discovered 4 large moons orbiting it. Those 4 bodies, Io, Europa, Ganymede, and Callisto, now called the Galilean moons, delivered a conceptual earthquake. Here were celestial objects clearly revolving around something other than the Earth, lending direct observational support to the Copernican idea that our planet might not be the center of everything. The era of robotic exploration opened with Pioneer 10 in 1973, followed by Pioneer 11 in 1974. Those missions gave us the first close-up photos and direct measurements of the Jovian environment, confirming the existence of radiation belts and detecting the ring system. Then came Voyager 1 and Voyager 2 in 1979, which transformed our understanding of the moons, particularly in spotting active volcanoes on Io, marking the first time volcanic activity had been confirmed anywhere beyond Earth. The real breakthrough in orbital study came with the Galileo spacecraft, launched in 1989 and arriving in December 1995. For nearly 8 years, Galileo circled Jupiter, making 35 orbits and conducting close flybys of all 4 Galilean moons. Before settling into orbit, it released an atmospheric probe that plunged directly into Jupiter's cloud layers, transmitting data for almost an hour before being crushed and vaporized by increasing pressure and heat. Among Galileo's most consequential findings, strong evidence for a liquid ocean beneath the icy crust of Europa. The mission ended in September 2003 when the spacecraft was deliberately steered into Jupiter's atmosphere, an act of planetary protection designed to prevent it from contaminating Europa or other potentially habitable moons in the event of system failure. Cassini-Huygens swung by in 2000 on its way to Saturn, and New Horizons did the same in 2007 en route to Pluto, both using Jupiter's gravity to slingshot themselves toward their destinations while gathering additional data along the way. The most sophisticated mission to Jupiter to date is Juno, launched in 2011 and inserted into Jovian orbit in July 2016. I've spent time reading through Juno's data, and let me tell you, the revelations keep coming. The spacecraft follows a highly elliptical polar orbit that brings it within about 4,200 kilometers of the cloud tops every 43 days, threading the needle between the planet's most intense radiation zones. Its scientific payload includes a magnetometer, a microwave radiometer for probing atmospheric composition far below the cloud layer, an infrared spectrometer, and JunoCam, a visible light camera that has produced some of the most visually arresting images of any planet ever taken. Building Juno to survive Jupiter required serious engineering creativity. The spacecraft's electronics are housed inside a titanium radiation vault weighing about 200 kilograms, offering protection roughly equivalent to a 9mm lead wall. Its solar panels, the largest ever deployed on a planetary mission, span a total of 60 square meters. Because that much surface area is necessary to generate adequate power at Jupiter's distance from the Sun. Mission planners initially expected the radiation to degrade Juno's instruments within 20 months, but the spacecraft has far outlasted those projections, prompting repeated mission extensions, with operations now running through 2026. What has Juno taught us? For one thing, Jupiter's poles look nothing like its equator. Where the equatorial region is dominated by orderly east-west bands, the poles are covered in chaotic clusters of cyclones, a stable pentagon of storms at the South Pole, an octagon at the north, formations that have persisted throughout the mission. Juno also revealed that the atmospheric bands and the Great Red Spot extend far deeper than anyone had anticipated, and that Jupiter's equatorial winds reach down approximately 3,000 kilometers, involving roughly 1% of the planet's total mass. The data also pointed toward a diffuse, fuzzy core rather than a compact one, suggesting Jupiter may have experienced a massive collision early in its history that mixed its interior layers. At mission's end, Juno will follow the same fate as Galileo, a controlled plunge into Jupiter's atmosphere, ensuring that no contamination from Earth ever reaches the pristine environments of the Galilean moons. Let me share something fascinating about Jupiter's moons. The planet has at least 79 confirmed satellites, a miniature solar system in its own right. Most of the outer ones are small, irregularly shaped objects captured by Jupiter's gravity long ago, moving in tilted and sometimes backward orbits. The interesting ones, though, are the 4 Galilean moons, each of which is a world complete enough to deserve its own dedicated mission. Ganymede is the largest moon in the entire solar system, bigger in fact than the planet Mercury, with a diameter of 5,268 kilometers. It's the only moon known to generate its own magnetic field, produced by a molten iron core. Its surface comes in 2 distinct flavors: ancient, heavily cratered dark terrain, and younger grooved lighter terrain that shows signs of tectonic reworking. Like Europa, Ganymede is thought to harbor a subsurface ocean, though it sits at greater depth and is sandwiched between layers of ice rather than directly beneath a thin crust. A thin oxygen atmosphere clings to its surface, produced when solar radiation and magnetic particles bombard the icy terrain and split water molecules. Callisto, the outermost of the four, is the third largest moon in the solar system, trailing only Ganymede and Saturn's Titan. Orbiting far enough from Jupiter to escape the intense tidal forces that heat its inner siblings, Callisto has remained geologically quiet. Its surface is one of the most heavily cratered in the entire solar system, a billion-year record of impact history preserved in ice and rock. The largest of these impact features, Valhalla, is a concentric ring structure 600 kilometers wide. Callisto may also have a subsurface ocean. Magnetic measurements hint at a conductive layer beneath the surface, though conditions there are far less dynamic than on Europa. Io occupies the opposite extreme. The innermost Galilean moon is the most volcanically active body anywhere in the solar system, with more than 400 active volcanoes constantly erupting sulfur and sulfur dioxide, painting its surface in vivid yellows, reds, oranges, and blacks. The energy source for all this activity is tidal heating. Io is locked in a gravitational resonance with Europa and Ganymede in a 1:2:4 ratio, which keeps its orbit slightly eccentric and causes continuous flexing of its interior. That flexing generates an estimated 100 quadrillion watts of thermal energy, roughly 25 times the total energy consumption of human civilization. Some of Io's volcanic plumes reach 500 kilometers above the surface, ejecting material that either falls back to the ground or feeds a plasma torus encircling its orbit. The tidal forces from Jupiter also create solid surface tides on Io. The ground actually rises and falls by up to 100 meters. Europa may be the single most exciting place in the solar system for the question of life beyond Earth, and I don't say that lightly. Its surface is smooth, among the smoothest in the solar system, covered in a web of cracks and ridges that betray the presence of liquid water underneath. The ocean beneath Europa's ice is estimated to contain more water than all of Earth's oceans combined, kept liquid not by solar heat, but by the same tidal forces that make Io a volcanic hellscape, just at a lower intensity. The surface is young, geologically speaking, with few impact craters, signs that active processes are constantly resurfacing it. Some regions show chaotic terrain, where the ice appears to have broken apart and refrozen, possibly stirred by convection in the ocean below. What makes Europa especially compelling is that its subsurface ocean satisfies all three of the basic conditions scientists consider prerequisites for life as we know it: liquid water, the necessary chemical building blocks, and an energy source. Tidal forces supply the heat. Cometary impacts may have delivered organic compounds, and some models suggest the ocean floor could host hydrothermal vents, environments where, here on Earth, rich ecosystems thrive in total darkness, completely independent of sunlight. Recent observations have detected water vapor plumes venting from Europa's surface, raising the remarkable possibility that we might be able to sample the ocean's chemistry without drilling through kilometers of ice. On October 14, 2024, NASA launched the Europa Clipper mission to conduct dozens of close flybys of the Moon, analyze its surface composition, and confirm the characteristics of its interior ocean. Many researchers consider Europa, ahead of even Mars, as the most promising candidate for extraterrestrial life in our solar system. Now here's where Jupiter's story becomes directly relevant to our own existence. I've spent decades studying this, and the cosmic shield idea is one of those things that the more you look at it, the more profound it becomes. Jupiter's gravitational pull is so strong that it regularly deflects or captures comets and asteroids that would otherwise be on trajectories toward the inner solar system, toward us. We got a front-row seat to this process in 1994 when comet Shoemaker-Levy 9, already captured into Jupiter's orbit, broke into approximately 20 fragments and slammed into the planet between July 16th and 22nd. The impacts left dark scars in Jupiter's atmosphere visible for months. Each impact released energy equivalent to millions of megatons of TNT, the kind of energy that would have caused a mass extinction event had it struck Earth instead. Computer simulations suggest that without Jupiter's gravitational presence, the rate of catastrophic impacts on Earth would be up to 100,000 times higher than it actually is. The extinction of the dinosaurs gives us a benchmark for what a single major impact can do to complex life. Multiply that frequency by 100,000, and the emergence of anything as complex as a human being starts to look nearly impossible. Some planetary scientists go further and argue that having a Jupiter-mass planet in the outer region of a solar system, positioned just right, neither too close nor too far, may be one of the prerequisites for the development of complex life on inner rocky worlds. In this view, Jupiter isn't just a neighbor, it's a guardian. Jupiter's influence doesn't stop at deflecting incoming debris. It appears to have shaped the entire architecture of the solar system during the early period of its formation. Many objects in the Kuiper belt beyond Neptune's orbit have orbital periods that are integer multiples of Jupiter's orbital period, a phenomenon called orbital resonance, suggesting Jupiter organized the outer solar system the same way a conductor organizes an orchestra. Some theoretical models go even further. According to what's called the Grand Tack hypothesis, early in the solar system's history, perhaps 5 billion years ago, Jupiter may have migrated inward from its formation location to roughly where Mars sits today, before being pulled back outward by interactions with Saturn. This inward then outward migration would have swept through the protoplanetary disk, redistributing material and fundamentally reshaping the orbits of the outer planets. Uranus and Neptune may even have switched places during this chaotic period. The timing of this instability may correspond to the late heavy bombardment, a period of intense cratering recorded in lunar rocks from roughly 700 million years after the solar system formed. Could life exist on Jupiter itself? It's a question worth asking, even if the answer is almost certainly no. The atmosphere does get warmer with depth, and at a level where pressure is about 10 times Earth's sea level pressure, temperatures are actually comparable to comfortable environments on our planet. Some scientists have speculated that if life were to exist on Jupiter, it would have to be airborne, floating organisms adapted to that specific altitude window. But as of today, there is zero observational evidence for life anywhere on or in Jupiter. The planet's environment, no stable surface, crushing pressures below a certain depth, extreme radiation above, is deeply hostile. I've spent a long time thinking about what Jupiter means in the larger story of our existence, and here's what I keep coming back to. This isn't just a planet we happen to share a solar system with. It's an active participant in the story of how Earth became what it is. Its gravity swept away debris that might have prevented life from getting started. Its position stabilized the outer solar system. Its formation history influenced where the inner planets ended up. And in its moons, it may be harboring the very life forms we've been searching for across the cosmos. Missions like the European Space Agency's JUICE, the Jupiter Icy Moons Explorer, are continuing the work that Galileo and Juno began, probing the Galilean moons for signs of habitability and mapping the deep structure of the planet itself. Every new dataset peels back another layer of mystery, and without fail, what lies beneath is more surprising than what we expected. That's Jupiter for you. The more you look, the more it looks back. Thanks for joining me today. I hope you walk away from this with that rare and wonderful feeling that the universe is even stranger and more magnificent than you thought this morning.